Hello friends, in the previous lecture we talked about the R and H parameters, described the R parameter transistor model, compared AC beta and DC beta, and in the case of common emitter amplifier we analyzed its operation, discussed a common emitter amplifier with voltage divider bias, performed its DC and AC analysis, and finally represented the amplifier by its DC and AC equivalent circuits. But there is more to be discussed about the common emitter amplifier to master it properly. So, in today's discussion we shall start from the voltage and current gains of CE amplifier, its attenuation, effect of load on the voltage gain, and finally the stability of voltage gain. We shall also be discussing the common collector and common base amplifiers in detail. Voltage gain. The AC voltage gain expression for the common emitter amplifier is developed using the model circuit shown in figure. The gain is the ratio of AC output voltage at the collector to AC input voltage at the base. AV is equal to V out over V in and is equal to Vc over Vb. Notice in the figure that Vc is equal to alpha AC into IE into RC and is approximately equal to IE into RC, and Vb is equal to IE into RE. Therefore, AV is equal to IERC over IE into RE. The IE terms cancel, so we get the expression for gain as given by this equation, where AV is equal to RC over RE. But this equation is the voltage gain from base to collector. To get the overall gain of the amplifier from the source voltage to collector, the attenuation of the input circuit must be included. Attenuation. It is the reduction in signal voltage as it passes through a circuit and corresponds to a gain of less than 1. For example, if the signal amplitude is reduced by half, the attenuation is 2, which can be expressed as a gain of 0.5 because gain is the reciprocal of attenuation. Suppose a source produces a 10 millivolt input signal and the source resistance combined with the load resistance results in a 2 millivolt output signal. In this case, the attenuation is 10 millivolts divided by 2 millivolts and is equal to 5. That is, the input signal is reduced by a factor of 5. This can be expressed in terms of gain as 1 by 5 and is equal to 0.2. Assume that the amplifier in figure has a voltage gain from base to collector of AV and the attenuation from the source to the base is Vs over Vb. This attenuation is produced by the source resistance and total input resistance of the amplifier acting as a voltage divider and can be expressed as attenuation is equal to Vs over Vb and is equal to Rs plus Rn total over Rn total. The overall voltage gain of the amplifier AV is the voltage gain from base to collector times the reciprocal of attenuation and is given by this equation. AV is equal to Vc over Vb into Vb over Vs and is equal to Vc over Vs. Effect of a load on the voltage gain. A load is the amount of current drawn from the output of an amplifier or other circuit through a load resistance. When a resistor RL is connected to the output through the coupling capacitor C3 as shown in figure A, it creates a load on the circuit. The collector resistance at the signal frequency is effectively RC in parallel with RL. Remember, the upper end of RC is effectively at AC ground. So, the resulting AC equivalent circuit is shown in part B of the figure. The total AC collector resistance is given by this equation, where RC is equal to RC into RL over RC plus RL. Replacing RC with collector resistance in the voltage gain expression gives AV is equal to RC over RE. Here RE is the AC emitter resistance and RC, that is R with lowercase subscript of C, is the total collector resistance. When total collector resistance is less than RC, because of RL, the voltage gain is reduced. However, if RL is much greater than RC, the total collector resistance is approximately equal to RC and the load has a very little effect on gain. Stability of the voltage gain. Stability is a measure of how well an amplifier maintains its design values over changes in temperature or for a transistor with a different beta. Although bypassing RE does produce the maximum voltage gain, there is stability problem because the AC voltage gain is dependent on the AC emitter resistance, that is RE. Also, AC emitter resistance depends on IE and on temperature. This causes the gain to be unstable over changes in temperature, because when an AC emitter resistance increases, the gain decreases and vice versa. With no bypass capacitor, the gain is decreased because RE, the emitter resistance, is now in the AC circuit. However, with emitter resistance unbypassed, the gain is much less dependent on AC emitter resistance RE. If emitter resistance is much greater than AC emitter resistance, the gain is essentially independent of AC emitter resistance because AV is equal to RC over RE. Current gain. The current gain from base to collector is IC over IB or beta AC. However, the overall current gain of the common emitter amplifier is AI is equal to IC over IS. IS is the total signal input current produced by the source, part of which is base current and part of which goes through the bias circuit as shown in figure. The source sees a total resistance of Rs plus Rn total. The total current produced by the source is 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 equal to Vs over Rs plus Rn total. The common collector amplifier. The common collector amplifier is usually referred to as an emitter follower. The input is applied to the base through a coupling capacitor and the output is at the emitter. The voltage gain of a CC amplifier is approximately 1 and its main advantages are its high input resistance and current gain. After completing this section, you should be able to describe and analyze the operation of common collector amplifier, explain the term emitter follower, determine output resistance, current gain, power gain, and lastly, will be able to describe the Darlington pair. An emitter follower circuit with voltage divider bias is shown in the figure here. Notice that the input signal is capacitively coupled to the base, the output signal is capacitively coupled from the emitter, and the collector is at AC ground. There is no phase inversion and the output is approximately the same amplitude as the input. Voltage gain. As in all amplifiers, the voltage gain is AV is equal to V out over V in. The capacitive reactances are assumed to be negligible at the frequency of operation. For emitter follower, as is shown here in the AC model, V out is equal to IE into RE and V in is equal to IE into RE plus RE. Here RE is the AC emitter resistance. Therefore, the voltage gain is given by this equation where AV is equal to IE into RE over IE into RE plus RE. The IE current terms cancel and the base to emitter voltage gain expression simplifies to AV is equal to RE over RE plus RE. Here RE is the parallel combination of RE and RL. If there is no load, then RE is equal to RE. Notice that the gain is always less than 1. If load resistance is much greater than AC emitter resistance, then a good approximation is that AV is approximately equal to 1. Since the output voltage is at the emitter, it is in phase with the base voltage. So, there is no inversion from the input to output. Because there is no inversion and because the voltage gain is approximately 1, the output voltage closely follows the input voltage in both phase and amplitude. Thus, the term emitter follower is used for this circuit. Input resistance. The emitter follower is characterized by a high input resistance. This is what makes it a useful circuit. Because of the high input resistance, it can be used as a buffer to minimize loading effects when a circuit is driving a low resistance load. The derivation of the input resistance, looking in at the base of the common collector amplifier, is similar to that from the common emitter amplifier. In a common collector circuit, however, the emitter resistor is never bypassed because the output is taken across RE, which is RE in parallel with RL. Rn base is equal to V in over I in and is equal to Vb over Ib and again is equal to IE into Re plus Re over Ib. Since IE is approximately equal to IC and is equal to beta AC into IB, Rn base is equal to beta AC into IB into Re plus Re over Ib. The Ib terms cancel, therefore, Rn base is equal to beta AC into Re plus Re. If load resistance is much greater than AC emitter resistance, then the input resistance at the base is simplified to Rn base is equal to beta AC into Re. Output resistance. With the load removed, the output resistance looking into the emitter of the emitter follower is approximately as follows. R out is equal to Rs over beta AC parallel with Re. Rs is the resistance of the input source. The output resistance is very low, making the emitter follower useful for driving low resistance loads. The Darlington pair. As you have seen, beta AC is a major factor in determining the input resistance of an amplifier. Beta AC of the transistor limits the maximum achievable input resistance you can get from a given emitter follower circuit. One way to boost input resistance is to use a Darlington pair as shown in figure here. The collectors of two transistors are connected and the emitter of the first drives the base of the second. This configuration achieves beta AC multiplication as shown in the following steps. The emitter current of the first transistor is given by this equation. IE1 is approximately equal to beta AC1 into IB1. The emitter current becomes the base current for the second transistor, producing a second emitter current of IE2 is approximately equal to beta AC2 into IE1 and is equal to beta AC1 into beta AC2 into IB1. Therefore, the effective current gain of the Darlington pair is beta AC is equal to beta AC1 into beta AC2. Neglecting Re by assuming that it is much smaller than the load resistance Re, the input resistance is Rin is equal to beta AC1 into beta AC2 into Re. An application. The emitter follower is often used as an interface between a circuit with a high output resistance and a low resistance load. In such an application, the emitter follower is called a buffer. Suppose a common emitter amplifier with a 1 kilo ohm collector resistance must drive a low resistance load such as an 8 kilo ohm low power speaker. If the speaker is capacitively coupled to the output of the amplifier, the load appears to the AC signal in parallel with the collector resistor. This results in an AC collector resistance of RC is equal to RC parallel with RL and is equal to 1 kilo ohm parallel with 8 ohms, and this comes out to be 7.94 ohms. Obviously, this is not acceptable because most of the voltage gain is lost. For example, if Re is equal to 5 ohms, the voltage gain is reduced from 200 with no load to 1.59 with an 8 ohm speaker load as shown by these calculations. With no load, AV is equal to RC over Re and is equal to 1 kilo ohm divided by 5 ohms, and it comes out to be 200. AV is equal to RC over Re and is equal to 7.94 ohms divided by 5 ohms, and the result is 1.59, and this is with 8 ohm speaker load. An emitter follower using a Darlington pair can be used to interface the amplifier and the speaker as shown in the figure here. The common base amplifier. The common base amplifier provides high voltage gain with a maximum current gain of 1. Since it has a low input resistance, the CB amplifier is the most appropriate type for certain applications where sources tend to have very low resistance outputs. After completing this section, you should be able to analyze the operation of common base amplifiers, determine its voltage gain, explain why there is no phase inversion, and determine output resistance, current gain and power gain. A typical common base amplifier is shown in figure here. The base is the common terminal and is at AC ground because of capacitor C2. The input signal is capacitively coupled to the emitter. The output is capacitively coupled from the collector to a load resistor. The voltage gain from emitter to collector is developed as follows, where Vin is equal to Ve and Vout is equal to Vc. So, Av is equal to Vout over Vin and is equal to Vc over Ve, and this becomes equal to Ic into Rc over Ie into Re parallel with Re, and is approximately equal to Ie into Rc over Ie into Re parallel with Re. If emitter resistance Re is much greater than the AC emitter resistance Re, then Av is approximately equal to Rc over Re, where Rc is equal to Rc parallel with RL. Notice that the gain expression is the same as for the common emitter amplifier. However, there is no phase inversion from emitter to collector. Input resistance. The resistance looking in at the emitter is given by this equation. Rn emitter is equal to Vin over In and is equal to Ve over Ie, and this again is equal to Ie into Re parallel with Re over Ie. If emitter resistance Re is much greater than the AC emitter resistance Re, then Rn emitter is approximately equal to Re. Emitter resistance Re is typically much greater than AC emitter resistance Re. So, the assumption that AC emitter resistance parallel with emitter resistance is approximately equal to AC emitter resistance, which is usually valid. The input resistance can be set to a desired value by using a swamping resistor. The current gain is the output current divided by the input current. Ic is the AC output current and Ie is the AC input current. Since Ic is approximately equal to Ie, the current gain is approximately 1. So, friends, here we come to the end of our discussion, and therefore, we sum up. A common emitter amplifier has high voltage, current and power gains, but a relatively low input resistance. A common collector amplifier has high input resistance and high current gain, but its voltage gain is approximately 1. A Darlington pair provides beta multiplication for increased input resistance. A common collector amplifier is known as an emitter follower. The common base amplifier has a high voltage gain, but it has a very low input resistance and its current gain is approximately 1. So, that is it for today. In our next discussion, we shall talk about power amplifiers.